All right, so we're going to start up a new research project, and it's pretty similar to the previous one that we did. We're going to answer some questions that came up when we submitted this paper to that some of the reviewers brought up, and they're interesting questions. Um, some stuff that I didn't realize that we could do, where I had thought about this to a degree, but um, they gave some ideas. I couldn't see how those ideas would work, but I think we have come up with a way that we'll be able to answer the question. And just a quick review. So this is the paper that we just published relatively recently about substrate inhibition of myoglobin and hemoglobin towards their pseudocatalytic properties. Okay, so why is this interesting? Well, myoglobin, hemoglobin, kind of probably already know about. It's an oxygen binding protein that delivers oxygen once it interacts with the oxygen in our lungs, delivers it to the rest of the body. Myoglobin is a very similar cousin, which accepts that oxygen from the hemoglobin. Okay, so both of these very, very similar. If I were to draw their structure, something like that, with an iron surrounded by a small molecule called a heme. That's myoglobin and hemoglobin. Now, hemoglobin is slightly different in that the activity of hemoglobin occurs in a tetramer like this. Okay, so you get these four different subunits of this globin with four heme groups, and they all work together as one. Myoglobin, so this is our hemoglobin. Myoglobin is basically a monomeric form of this same thing. So very, very similar in structure, but it works individually. Okay. And their role is to bind and deliver oxygen, and this one is to store oxygen in the muscles or in the tissue. Okay. However, they have this property, which this catalytic ability, which is not claimed to be natural, called, and so it's called a peroxidase activity, and they call it a pseudo peroxidase because people don't think that hemoglobin and myoglobin were kind of evolutionarily chosen for this role, right? They think that it's just a side effect, basically because it has an iron heme in it. And we've done some studies that kind of bring that into question with our previous publication about this work. And while we were doing that one, we learned that if you have high concentrations of of hydrogen peroxide, you actually inhibit this pseudoperoxidase activity. And that's what this paper is about. So the myoglobin and hemoglobin, let me draw the iron over here for a second so that I can show it to you better. Hydrogen peroxide, H2O2, gets coordinated by the iron in myoglobin and hemoglobin. And then we use a green dye called ABTS. ABTS will donate an electron once the hydrogen peroxide is coordinated to the iron. When that occurs, we get two hydroxide radicals that leave. Now, this might not be the exact mechanism, but it looks like we're getting two hydroxide radicals that leave from this being cleaved from an electron being donated. Once ABTS donates that electron and becomes ABTS with a positive charge like that, that species, this one is green, right? This one is a very, very light green, and at the concentrations we use it, it's pretty much colorless, okay? So you can monitor how much color appears and how fast it appears, and it'll tell you how fast the myoglobin or the hemoglobin, your catalyst, is breaking down hydrogen peroxide. Okay, so that's the way that we tell how active this species is. Now, in this paper here, we changed the concentrations of hydrogen peroxide and checked how the activity of the pseudoperoxidase behaved, how the pseudoperoxidase activity of these catalysts, myoglobin and then hemoglobin, behaved. Okay, so this here, it shows the average rate, the activity versus time, no, sorry, versus concentration of hydrogen peroxide. And you see that as you increase concentration of hydrogen peroxide, the activity goes up. but then it starts to come back down. Okay. Now, this graph here was collected when the hydrogen peroxide, this concentration, was soaking with the catalyst, either myoglobin or hemoglobin. In this case, this is myoglobin, right? For about a minute or two. And then we added the ABTS to see how much activity it had. Okay. If we add the ABTS and the hydrogen peroxide, but not the myoglobin or the hemoglobin, no green color, obviously, but then we add the myoglobin or the hemoglobin, the catalyst, the reaction can occur right away. And it will begin right away. And you'll never see any of this substrate inhibition. You won't see any of this substrate inhibition. There are some interesting things that you'll see if you look at the color of the green color, right, which is we monitor using a spectrometer at 730 nanometers versus time. You'll see that this will go up the amount of green color because of the conversion between ABTS reduced to ABTS oxidized. You get the green color. The green color will go up over time, but then gradually you'll begin to see that this slope slows down. And it could be that that slowing in that slope is due to damage to the protein. And that's something that we might look at in this new work as well, this new study. That'll give us more insight into the timing of the study, possibly. But the real key component of this new study is that we're going to use size exclusion columns to separate the hydrogen peroxide from the catalyst, myoglobin and hemoglobin, at different time points, and then test how active that myoglobin or that hemoglobin is. Okay, so for example, if we took myoglobin and we tested its activity with the ABTS, with the hydrogen peroxide, right? Different components necessary. We check the activity, and that means we look at the slope of this line right there, the slope at the beginning there. We fit it, y equals mx plus b. We find out what the slope is, and that number will tell us how much green per second, or per second here is usually where we're at, seconds. And then we'll be able to tell how active the catalyst is. So if we take myoglobin and we check its activity, right, then we'll say the activity, let's see, maybe we'll call it activity is X amount of activity if you just take myoglobin and hydrogen peroxide by itself. Okay, the myoglobin interacts with hydrogen peroxide, the reaction occurs, and you see X amount of activity, which again would be measured numerically by the slope of that line there. Okay, then what we're going to do is take hydrogen peroxide and myoglobin and then wait 2 minutes, right? And then we can check its activity. And we know what will happen here. We've done that in this paper here. We see that if you look at this figure over here, we see that this is the exposure time to hydrogen peroxide. So initially, 100% of your activity is there. For myoglobin at pH 5, the red one here is hemoglobin. After a few minutes, you lose 20%, and the activity decreases as you allow the hydrogen peroxide at a fixed concentration to soak with the myoglobin. Okay, so we're losing activity, and we know at which rate we'll lose activity relative to if you wait 20 minutes, you're losing this much. After 40 minutes, you've lost basically all your activity. Your activity is not coming back. Okay, hemoglobin even loses activity much faster, which is very interesting, and that's part of the paper, this paper here. But the question is, what if we allowed the myoglobin or hemoglobin to soak with hydrogen peroxide at this same concentration maybe for this many minutes, looks like about 3 minutes there. And then before we tested its activity, we removed all the hydrogen peroxide from it and then took the myoglobin to see if it had regained its activity because now the hydrogen peroxide was gone. Okay, so that's what we're trying to see if we can test. Okay, so we would wait 2 minutes and then remove any hydrogen peroxide, and then check the activity. Okay. Now, my hypothesis is that along this slope here, after a certain amount of exposure, there will be a point where you can't recover activity because permanent damage has occurred. But I'm expecting that maybe early on, maybe in this range here, there is a recoverable amount of activity. And maybe you never recover 100%, but maybe you always go up to a percentage based on how much time you've allowed it to react, suggesting that possibly there's a lot of myoglobins. And as soon as they're introduced to hydrogen peroxide, some will completely lose their activities, while others will be slightly damaged, right? And then if you remove the hydrogen peroxide, the ones that are slightly damaged can come back, but the ones that are permanently damaged can't. This permanent damage might actually be a polymerization. And if you read through that paper, or if you were part of it, you remember there was a paper that kind of talked about the polymerization, and that was a hypothesis that we thought about. Another thing, so basically that's going to allow us to wait different amounts of time with the hydrogen peroxide, hopefully completely remove the hydrogen peroxide, and then test the activity of that catalyst and see if it's compare it to what it was initially. Okay, so that would be one set of experiments, waiting different amounts of times, removing the hydrogen peroxide, and testing the activity of the myoglobin. Another set of experiments would be waiting a certain amount of time and then adding something like vitamin C. Because one of these papers said that ascorbic acid, vitamin C, can regenerate myoglobin. They showed some artifacts that suggested that's there. I kind of don't feel like it was really evidence. I think they were seeing something else. But this should clean up that and bring us to that answer. Let us know whether or not something like hydrogen peroxide or maybe some other reducing agent would provide the ability to regenerate myoglobin or hemoglobin, those catalysts, in the presence of hydrogen peroxide. So we would take it, add some hydrogen peroxide, wait for a certain amount of time, and then add some vitamin C, and just see and then we would clean it up, remove all the hydrogen peroxide, all of the vitamin C, take the myoglobin again, test its activity, and see where we're at. We could do experiments where we added the hydrogen peroxide at the same time as the vitamin C. We could do experiments where we have vitamin C already, and then we add hydrogen peroxide and see if the hydrogen peroxide can still do damage to the myoglobin. All this is good because ABTS, the chemical that we're going to use to determine that turns green for us, right? That is a strong reducing agent as well. And I think we have already seen in some of our runs that in the presence of ABTS, as long as you have a constant source of electrons, then the myoglobin does not get nearly as damaged. All right. So, for example, this amount of energy activity loss, right? Just after about 5 minutes here, or about 3 minutes. After about 3 minutes, you see a loss of about 20% of your activity. Okay. But if you just take the enzyme by itself and run the activity or run the assay for 3 minutes, you can still maintain a significant amount of activity. So to me, that was suggesting that perhaps what's happening is as the ABTS is around, acting kind of like vitamin C, an electron donor, it won't allow the hydrogen peroxide, or maybe it's these hydroxide intermediates that the vitamin C or the ABTS is cleaning up, right? But this will also be a way to test that, right? We could introduce ABTS, allow the reaction to occur for a while, strip it from all the hydrogen peroxide and the ABTS, take the catalyst, and then start over with it and see where we're at, okay? So how are we going to do this? How are we going to clean up our myoglobin? Okay, it's we're going to use what's called gel filtration material. Okay, so essentially, if you look at it under a microscope, really strong microscope, what you'd see is a little piece of kind of gel with little tiny holes in it, little tiny holes, and you're going to put this gel into a syringe. So we have a syringe. We still recording? Sorry about that. We're going to take a syringe, all right? A syringe, and we're going to put, first of all, a little bit of glass wool here. It's basically a stopper to prevent this material. Now, if you just have a container of this material, what it's going to be in a 50 milliliter conical vial, like we have in the lab, and it just looks like a little bit of white mush at the bottom of the container. But you stir it up, you swish it around, and then it makes a slurry, and then you pour it into here. And when you do that, the water or the buffer, or whatever the solvent is that it's in, comes through, but this material begins to pile up, and you get this gelatinous kind of like what you think you would see if you had ground up Jello, right? Just some gel-like beads all in that space, okay? And what these gel beads are small pieces of plastic-like material with little holes, and the holes are smaller than the myoglobin itself, okay? But they're not smaller than the hydrogen peroxide, okay? They're not smaller than the buffer or the ABTS, okay? So what should happen is if I take a mixture of maybe the catalyst, we'll use myoglobin, we have some hydrogen peroxide that it was soaking in, and maybe in this experiment here we had some vitamin C as well, okay? So we had these things in here, we soaked it for a certain amount of time, and then we take this and put it onto this column here. And then we put it into a centrifuge and just spin it for a couple of seconds. And what happens is, because the myoglobin can't, or the catalysts can't fit into these beads, they just find their way through this really fast, and they just plop out at the bottom. So you have a little container here, and you collect them. Okay? The salts, the small molecules, the buffers, the hydrogen peroxide, the ABTS, it all goes into these pores, and on its way down, it takes a really long time because it's stuck in all sorts of different pores as it's heading down. And so it takes a really long time to migrate down after it's been, when you try to centrifuge it. So the result is this stuff flies right through any water that's left, and whatever solution you had this in initially, so we'll store this in some buffer, it will come out with the catalyst, the myoglobin. So the myoglobin, the large things will come out very quickly, but the small things will get stuck in the resin, and they'll take a long time to get through, and we won't let them get through. Okay? So we can take this sample, test the activity of it before we put it through, and now it should be free from the hydrogen peroxide or ABTS or anything else that we are trying to interact with. And then we can test the activity of this sample here. We take this myo and test its activity and see if we've lost activity or if there's a way for us to regain activity using the vitamin C and so forth. Okay, so that's how this experiment, this work is going to go. So very similar in how we measured the enzyme activity, very similar as before, but now we have this size exclusion tool, which will allow us to separate myoglobin from any other small molecules and test it before and after and learn about if we've lost activity, the timing of how long it takes to lose activity, if the activity was recoverable with any other reductants like vitamin C or ABTS, its impact on the activity as an example. All right, so we're going to create a column that will separate all the small molecules from the protein and deliver the protein into a sample of just buffer or water or whatever solution we want to deliver it into. Okay. To do this, we take one of these syringes, right? And in the bottom here, I've layered an amount of what we call glass wool. The glass wool is kept in this drawer like this. All right. It's made of glass, so it'll bother your fingers if you crunch it up too much. Getting it a little bit down in the bottom there is a little bit tricky sometimes, but you want a good layer. You can see the layer that I have there. You'll be able to tell whether the layer is working. What it's going to do is catch the resin that we're going to put into this little column. So the glass wool, you can reuse it though. So as soon as you get one with some glass wool in it, it should be good to go. You can use this side here to kind of squish it down, make it nice and flat, your little frit, we'll call it, a little glass wool frit. You can put some water in there to kind of help pack it down as well. After you get this, then you're going to fill this up with some resin. So the resin is kept here in the fridge it's going to be soaking in a vial, one of these vials. Okay, so here it is. This is, you can see it's a slurry of this resin material. Okay? And then I'm going to take this and I'm going to, while it's kind of being slurried, because if you let it settle, it'll settle pretty fast. So you gotta kind of get it slurried, and then you pour it into that little space there. Let's do that over here, over this lid right here. So if I spill, and as you pour, the resin will collect and the water will go through. So then I just pour like this. Okay, and then you can see the water is dripping out. That's actually, we have this suspended in some buffer. Okay, so I can see that now the resin is right about to there. Is that okay? That's more than plenty. We only need to have about maybe at the 1.5 side, okay? So we want to get better at doing this. We don't want to waste resin. We have a limited amount. We could buy some more, but I could, pour some back right now if I wanted to. There, you can see pour some back, and then I can kind of go like that. But once you do that, then you can see that it kind of gets some air pockets, which you can't have. You can take this sort of thing and do a gentle spin like that. More tough and gentle, okay? So now I'm about 2 mils, so still a little bit too much. I'll have to get better at it. Now it's kind of dried out a little bit, so I have to tap it to make it. So I've lost it all there now, okay? But now I can try again. I'll add this liquid back in there. So you see that we want to get good at this and pour ourselves. Try again here. That's pretty good. Maybe a little bit more because it's going to compact down when we centrifuge it. So I'll just a little bit more there. That's probably pretty good. So I'm about to the 1.5 line. Okay? You can see the resin there. Now, right now, the resin has a significant amount of moisture with it, but the moisture has stopped leaking through. It's kind of being bound by that resin. Okay? And now we take this to the centrifuge. Okay, so now that I have my resin that I've poured, right? I haven't centrifuged it yet, but I'm going to centrifuge it. And the way that I do that is I get one of these bottles right here, make sure it's completely empty, all right? When you poured your resin and you let it drip, you made sure that none of the resin was coming past the frit. Because if anything is coming past the frit in terms of this resin, that's a problem. The water should flow through, the solvent solution that's there should flow through, but not the resin. Okay, so I put this in here like this. I use this little knob here to open, turn left to unlatch it, and then I can have access to the centrifuge here. There's 6 spots here. One of them is going to have this little thing in there as a balance for the one that I'm putting in there. So these two are going to be across from each other. This has some suction cups, so it should hold pretty good still. But if it wobbles weird anytime, turn it off right away, okay? I close the latch like that, and once this is closed, then this can turn on. And here's how I turn it on. As soon as I hear it start turning, as soon as I turn this knob, I count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I turn it off, okay? And then I can open it. Now, be very careful here. If you want to be brave, you can slow it down just gently like that. Okay? Make sure if you're not brave, don't do it. All right? So now I've spinned out all of the liquid that was in here. Now there's still some in here. And when I put my protein in solution on here, the protein will fly through, but the liquid will exchange. Anything that's small in there will get stuck in here. So all of the moisture will get stuck in here and displace any liquid that's in here, and the protein, anything that's large, won't get stuck in here and will come through in whatever the liquid is in this phase right now. Okay, so this stuff here, I can keep it. I'm going to put it in this little lid here, and I'll add it back to the solution. It's buffer, you know. I'll add it back to that slurry later. Okay, now this is ready, and we didn't lose much volume, so that's good to know. If you pour it to about 1.5, it's going to stay at about 1.5. So now this is ready, and what I'm going to do is I'm going to take 100 microliters of my protein, for example. Now this might have been 100 microliters of the protein that was soaking with hydrogen peroxide. And then you would take 100 microliters of the protein soaking with hydrogen peroxide, and at the exact right time, you're going to gently pipette it onto the top of our resin, right? And when you do that, you'll see that this little portion right there becomes brown with the color of the myoglobin, right, or the hemoglobin. Okay, now we go back in here again, and now we're going to only spin it for about 4 seconds. So I turn it on, 1 1000, 2 1000, 3 1000, 4 1000. Let it stop like that. Okay. Again, slow it down gently. Careful when you do this. All right. And now we'll see that the brown color came all the way through because the pores of these beads are smaller than the size of the myoglobin. So it can't fit in those beads and it just slides right through. Everything else that was with this, like the hydrogen peroxide, ABTS, anything else, vitamin C, whatever else we had initially, will have gotten caught on this resin up here, okay? So, okay, now that you have your protein ready to test its activity, I'm going to show you how to test the activity of the protein running an assay. A lot of you have already done this, but you might want to have a quick refresher. All right. So we use the spectrometer. So we get one of these spectrometers in this drawer. Okay. The software that runs the spectrometer. There's a couple of options. Logger Lite is one that's good for PCs. Macs, you might have to search this specific brand here and find out what's good for running it on a Mac or for your specific scenario. Chromebook might be different as well, but Logger Lite is the one that I prefer. It's not the only one. It's not the only one that works. But plug this in, and then when you plug it in, you should see some indication that the computer has been connected. For Logger Lite, the rainbow shows up there. Okay. I'm going to set up an experiment. I go into experiment here, go down to data collection, and then choose mode. I choose time-based, okay? And duration, we usually do about 100 seconds. That might vary based on the type of experiments. We're gonna take one sample every second. I'm gonna say done here. And then I'm gonna go into the wavelength up here, and I'm going to choose the wavelength that corresponds to ABTS. So it's about 730. So any of these ones that's about 730 right there will do. And then I say okay. All right. And to start off, it's going to ask for a blank. So I'm going to put just a little bit of water into this thing here to be a blank. So let me fill this up. About 7/8 full like that. All right. I'll put it into this cuvette here. Hopefully you've had some training with cuvettes and spectrometers from GenChem, knowing that there's a specific way that it has to be aligned, right? So this is in there. I can push collect here, and when I push collect, it'll probably prompt me to do a warm-up. And that's fine, you can let it do a warm-up. Looks like my computer wants to be plugged in, so. Okay, so I'm going to skip the warm-up for now, and I'm going to say finish calibration. I make sure that I have my blank cuvette of just water when I push finish calibration, and let it do its thing here for a second. And as soon as finish calibration is done, then I can push OK. I push OK, and now it's going to start collecting data. For this one, I don't need to have this data necessarily, so I'll push stop. When you actually are collecting data, you're going to, that was the blank and we blanked it, but now when I actually run an assay, I follow the directions specific to my experiment, which is going to be getting an amount of buffer, an amount of salt, an amount of buffer, salt, water, myoglobin, and ABTS. Okay, all of those are in the fridge over here. Oh, and also hydrogen peroxide. Okay, so I'm going to get these here. I see the tops there labeled. There's different kinds of buffers. You might be using MES or HEPAS buffer. All right. Okay. Here's some distilled water for us. It's the same that comes out of the white faucet over there. Here's our salt, magnesium sulfate. Here's the hydrogen peroxide. Sometimes you have to make your own hydrogen peroxide fresh. Okay. So I have all the components that I need here. Okay. So I'm going to just run a quick experiment by putting in an amount of, so I would be following the rules on my specific spreadsheet that I had been given, right? But I'll be adding in a certain amount of buffer, okay? New tips, a certain amount of salt, magnesium sulfate here. Okay. Follow the directions again and add a certain amount of hydrogen peroxide. The order does matter for some things, not for all the things. The order really matters for the hydrogen peroxide, the myoglobin, and the ABTS. And so you do have to pay attention to your specific instructions to see what your instructions are telling you to do. But now I'm ready to add, I've added everything but the ABTS and the myoglobin, okay? So before I add the ABTS and the myoglobin, I get a little bit of this parafilm here. Here are the scissors. I cut off a little square of the parafilm. This is just a tool to help me mix. I hold it right there and I get a good mix right there. So now everything is homogeneous before I add the ABTS, okay? So, get a new tip here, add my ABTS. Use that same parafilm to homogenize that. Now, everything's in here except for the myoglobin, or the protein, either hemoglobin or myoglobin, okay? I can make sure that there's no drips or condensation on the surface that's going to be exposed to the light there. So I'm ready to add my myoglobin. I do need to add the myoglobin in such a way that it's added quickly, and I shake it quickly, and then I start the spectrometer. Now, again, that might vary in different experiments. Okay, so new tip here. Here's my sample ready to go. Here's my catalyst. Okay. I don't know if this is myoglobin or hemoglobin. I just took from extra from the fridge over there. But as soon as I add this, then this should start turning a darker green. Okay. So I'm getting ready to push collect here. All right. Now when I push collect on mine, it says, oh, so at that time I didn't do it. So if I push stop, let's see, sometimes when you push collect, it gives you the option to erase the previous data. So I just want to be ready to make sure that If you collected a whole data set and then you push collect again, it'll say, do you want to save the data? And that'll add extra time. So if you know if it's going to ask you if you want to save the data, you can push collect so that it's just a one click away before it starts actually reacting. So I know I'm one click away now if I push the collect button. So I'm going to be ready. I add the catalyst. I take this, shake it up, right? And then I push collect like that. All right. So now, I don't know if you can see, but it was already turning green. And this is telling me how the depth of the green color versus time. And I can see that it's getting greener and greener and greener. And that's slope, which is this color can be related directly to the amount of hydrogen peroxide that's being consumed, the amount of ABTS that's being produced versus time. So that's a nice straight line. I wouldn't need to go any more than that. If I wanted to go for 100 seconds, I could, but I got a lot of data there. I got 30 points that look like it's very linear, so I can push stop. And now I can take this data, highlight there, after I push stop, shift, and highlight there, Control C, and then go to my spreadsheet which I'll be following, right? Paste my data in the right spot, so it'll say exactly where to put it in your spreadsheet, and then you can take a scatter plot, create a scatter plot. You could right click on that, add the trend line, for example, and then the slope there, 0.0097, is telling you how fast the reaction occurred, and that gives you an indication of the condition of the enzyme. All right. We soak it with hydrogen peroxide for a minute. We run it through the column. The hydrogen peroxide goes behind. The hemoglobin or myoglobin comes out the bottom. We test it and compare that to this one here and see if we've lost activity because of that soak with the hydrogen peroxide, or if the hydrogen peroxide damage was reversible. And so once it came back in to our solution, it was okay, and the rate was the same. Okay? All right, so you have the ability to perform these reactions now as well. Okay, great.